you. Thank you. Very nice introduction. So I'm going to talk to you about searching for life elsewhere in the universe with trapist beer and speculoos, which could seem weird, but this is really what we do. So since I'm a kid, I have this question in mind: is there other extraterrestrial life forms elsewhere in the universe? Is there other inhabited planets elsewhere in the universe? And now we are really close to getting an answer to this question. And it's no more science fiction, it's real science. So to answer this question, we need to detect planet around another star. And it has to be rocky, it has to be within what is called the habitable zone of the star, so not too close, not too far from the star, to make possible the existence of liquid water on its surface, because we think that life really needs liquid water, at least on Earth it does. And then we have to analyze this planet, and not just detecting it, but analyzing its atmosphere, its atmospheric composition, and search for traces of life, what we call biosignatures. So we need to see some disequilibrium in its composition, atmospheric composition, that indicates that something is going on the surface, something that has a biological origins, like photosynthesis, for instance, on Earth. And so, to do this, a good way, a promising way to do this challenging task, because these planets are light years away, we can't just study them like we study, for instance, Venus or Mars. It's to catch planets that pass in front of the stars, that transit the stars, like we say. And when they do this, we have the thin annulus of the atmosphere that also pass in front of the star, and a fraction of the light emitted by the star in our direction is going to pass through this annulus, and is going to be filtrated by the atmosphere, by this atmospheric annulus. And we are going to make spectra of the star, so we are going to analyze its light, its distribution of light as a function of the wavelength, of the color, and we are going to compare these spectra taken outside the transit and when the planet is there, and we are going to see some differences that tell us about the composition of the atmosphere. And so this principle could work now for planets that are orbiting very nearby stars, but it won't work for Earth-sized planet, except if the host star is very, very small. Because the bigger the star, the more it dilutes the signal from the planet. The more photons you have that do not pass through the atmosphere. And so with current technology, we rely on the detection of planets transiting very small stars. If we want to detect and study an inhabited planet, or at least an habitable planet. And so we have this brilliant idea in my team to make a project. First of all, we wanted a cool name, so we named it Speculoos. Then we had the idea to apply this name to a search for habitable planet eclipsing ultra-cool stars, which make a very far-fetched acronym, but this is really what we want to do. And so, with this project, we want to observe the nearest, what we call ultra-cool stars, are very, very small stars, really tiny, 10 times smaller than the Sun, and we want to search for planets passing in front of them. And so, to do this, we need quite a big telescope, but before asking the funds for this project, we did a prototype on our telescope, robotic telescope located in Chile, which is called TRAPPIST. And so, you see real TRAPPIST there, and of course, the name of this telescope is a kind of tribute to the Belgian fine products that are there. They are not all Belgian, but most of them are Belgian. And so TRAPPIST is the acronym of Transiting Planets and Planetesimal Small Telescope. Again, very far-fetched. But it means that we study exoplanets with it and also comets. And from 2011, we use it as a prototype to search for planets eclipsing the nearest, smallest stars. And in 2016, we have been successful with our first detection of an amazing system of 7 Earth-sized planets, all orbiting the same star, all very close to the star, But they are so close to the star that, in fact, you would see the star from the surface of this planet like 10 times bigger than we see the Sun. Despite the fact that this star is 10 times smaller than the Sun. So we're really talking about distance which are something like 100 times smaller than the distance between the Earth and the Sun. But still, because the star is so small and cool, they receive this planet more or less the same amount of light than we receive on Earth from the Sun. So this planet could have some liquid water on the surface, in theory. So the way we detected this planet is illustrated here. It's called the transit method. So we observe the system and we wait for the planet to pass in front of it. But we don't see the planet. What we do is just to measure the evolution of the brightness of the star as a function of time. We call this a light curve. And when we have a planet passing, we see a drop of brightness. And this is how we detect these things. Of course, the planet on its orbit, it's something periodic, it has to come back. So we can verify it's a planet because it will come back after each orbit, after each year of this planet. And so our data, because it's something related to data here, I understood. So our data look like this. So our telescopes are always observing the same field of the sky, the same patch of the sky with our target within it. So here you have an image taken by one of our telescopes, which is called Europa, located in Chile. And so our target is here in the middle. This is in fact a stack of all the images we did for the night. So we observe the full night and we wait for the brightness of this star here to drop because the planet is passing in front of it. And if we see this, we open views, of course. And so you see our images are not so nice at what you see in a press release. So you see only the stars, you don't see the planets. And even the images is quite, well, not noisy, but you see some patterns here, which is called fringing, which is because we observe in the near infrared with a silicium detector, and the silicium is relatively transparent to near infrared. And so you have the photons that some of them are reflected in the back of the detector, and they interfere and they make this fringing pattern, which does not bother us for detecting planets. Okay, let's zoom on this thing, on this star. It is TRAPPIST-1, by the way. So this is TRAPPIST-1, this is other stars in the field. And what we do is to just measure the brightness of the star. So we just measure the counts in the image. We just measure the photons which are detected on our camera for within this circle. We call this aperture photometry, so it's very simple. Very small, clever way to measure the flux, but they don't work as well as this simple method. So we just measure the flux in a lot of apertures, close to already. We also do it for comparison stars, and what we get at the end is this. So you have the evolution of the flux as a function of time. In green you have the TRAPPIST-1, in blue you have the comparison stars. You see nothing, basically just noise. Because we observe through the atmosphere, which is something which is extremely inhomogeneous and unstable. But when we divide the green one by the red one, we get this. And so we correct most of the atmospheric effect, and what you see is the real evolution of the star with this drop of brightness. And this is when we open the ears. And so at the end, we analyze this data by fitting models in this data, so eclipse models, which are based on geometry, on Kepler dynamics. The approach that we use is a Bayesian approach. So basically, we use prior knowledge on the star itself, on the system, to constrain better the parameters. We use methods called Mark-Rochet and Monte Carlo. Our models also include the variability of the star, because the star is not something completely quiet. You have some effects from the star itself, not from the planets. You have systematic effects, because in real data, of course, you have systematic effects. And at the end, we get the parameter of our planet. And the most interesting one in this analysis will be the radius. because the signal is really proportional to the size of the planet. The bigger the planet, the bigger the drop of brightness. And we are all waiting for this giant telescope to be launched next year because it will enable us to study the atmosphere of the TRAPPIST planets. It's called the James Webb Space Telescope. And the data of the James Webb Space Telescope won't be images, but spectra. So you will have a dispersion of light in one direction on the detector as a function of wavelength. And so what you see here is one of the detectors of James Webb. So here it's still the space direction. And here the light was dispersed as a function of wavelength. So we are in the infrared here, between 3 and 5 micron. And if you collapse this in one direction, in the spectral dimension, you have the spectra of measure here. This drop here is not real, it's just the response of the detector, which is null there in this wavelength range. And what we are going to do is to measure for plenty of beams in wavelength the light curve, so the evolution of the brightness of the star. And what we are going to see is that the drop of brightness varies with wavelength. In wavelength for which you have, for instance, a strong absorbance, the atmosphere, for instance, ozone, if you are dreaming about an inhabited planet, ozone would be a usual suspect. You would see an increase of the apparent size of the planet just because the atmosphere absorbs more than in other wavelengths. And so this is a kind of data. These are simulation of transmission spectra, like we call this, that will be taken by James Webb. And we hope that in the real life we will get this kind of structures that will tell us that there is some oxygen on this planet, ozone being the byproduct of the photolysis of oxygen in the atmosphere. And at the end, searching for life elsewhere in the universe is within reach. Even beer drinking forms of life, like this one, is no more science fiction. This is something that can be done, and we'll be happy to answer your question after the hot talks.